Hi, in this video I assume you've worked with exponents before. So what I'm going to do in this video is try to explain some of the reasoning behind some of the exponent rules you've learned in your algebra course. And we're going to be dealing with integer exponents. So let's take some examples. Let's take a base of 2 and raise it to the first power. Well, that's just 2. And 2 to the second power, also called 2 squared, that means 2 times 2, which is 4. 2 to the third power means 2 times 2 times 2, which is 4 times 2 comes out to 8. Okay, you may have learned this rule in your algebra course. If you take a non-zero base, such as 2, and you raise it to the 0 power, that's defined to be 1. Okay, which is a little strange, but we're going to explain why it's 1 in just a bit. Okay, likewise, if you had a negative exponent, such as 2 to the negative first, that's defined to be 1 over 2 to the positive first, or 1/2. Okay, another example with a negative exponent would be 2 to the negative 2. That's defined to be 1 over 2 to the positive 2, or 1/4. And one last example, 2 to the negative third power is defined to be 1 over 2 to the third power, or 1/8. Okay, but why? Why do we get these answers of 1, 1/2, 1/4, and 1/8? Well, I'm going to give you a couple of reasons. First, I'm going to try to organize this information, these examples, in such a way that it makes sense to you and it's easy to remember. So what I'm going to do is draw a number line marking 0 in the middle, and as usual the positive numbers go to the right and the negative numbers go to the left, and under each integer marked on this line I'll put the corresponding power of 2. So right under 3 I'll put 2 to the third power, and right under 2 I'll put 2 to the second power, and so forth. So let me put all these powers of 2 in the same order as the integers on the number line. And underneath each power of 2, let's put the answer that we discovered above. 2 to the third was 8, 2 squared is 4, 2 to the first is 2. And for some reason, 2 to the 0 is 1, 2 to the negative 1 is 1/2, 2 to the negative 2 is 1/4, and 2 to the negative 3 is 1/8. Okay, look at these answers here. Okay, let's look at them from right to left. Starting at 8, every time we take a step to the left, can you describe what's happening to get from the 8 to the 4 and from the 4 to the 2? Well, one answer to that is we're dividing by 2 every time we take a step to the left. Okay, we're taking 8 divided by 2 to get to the 4, and 4 divided by 2 to get to the 2. And so if you were going to actually come up with some reasonable answer for these other exponents here, you might continue that pattern of dividing by 2. 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. So it seems reasonable to define 2 to the 0 as 1. And if we take 1 divided by 2, we get half. And if I take a half divided by 2, I get a fourth. And if I take a fourth divided by 2, I get an eighth. So we're continuing that pattern of dividing by 2 as we go to the left. So that gives these answers for these integer exponents a little more meaning for us now. Also notice if you go from left to right, you're multiplying by 2 each step you take. Okay, for example, starting at the 2, 2 times 2 is 4, 4 times 2 is 8. But that works all across the number line, starting from the far left. 1/8 times 2 is 1/4. 1/4 times 2 is 1/2. 1/2 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. And 4 times 2 is 8. So we've got this nice pattern of multiplying 2 as we go to the right, dividing by 2 as we go to the left. So this seems natural. This seems natural to me to have these answers for these integer exponents. Okay, but I'm going to explain it one more way, okay, to kind of give you an airtight argument as to why we define these integer exponents the way we do. Okay, so for example, I'm going to base this all on a law of exponents I hope you've seen before. If you have a base raised to a power times the same base raised to another power, do you remember what you get? You get that same base again with a power of m plus n. Okay, you add these exponents together. Okay, if you haven't seen that before, there's a really simple reason why this is true. I'm going to illustrate it with an example. If I had 2 to the second times 2 to the third, according to this rule I should get 2 to the 2 plus 3, adding these two exponents here, which is also 2 to the fifth. So 2 squared times 2 cubed should be 2 to the fifth according to this rule. And if you write down what 2 squared is, it's just 2 times 2. And if you write down what 2 cubed is, it's just 2 times 2 times 2. And we're multiplying those together. And if you write down what 2 to the fifth is, you've got 5 2's multiplied together. And this makes perfect sense because I've got 2 2's and 3 more 2's here. So I've got 5 factors of 2 altogether. So this rule actually works. Anyway, based on this rule, we can explain these integer exponent rules. Okay, for example, if you didn't know what 2 to the 0 was, you could figure it out like this. Take 2 to the 0 times, just for an example, some other power of 2, like 2 to the fifth. According to the rule about adding the exponents, we would get 2 to the 0 plus 5, which is also 2 to the fifth. Okay, so 2 to the 0 times 2 to the fifth equals 2 to the fifth. So what should 2 to the 0 be equal to? We've got something times 2 to the fifth equals 2 to the fifth. Well, what number multiplied by 2 to the fifth would give you 2 to the fifth? 1, of course. Okay, you can actually algebraically solve for 2 to the 0 by dividing both sides by 2 to the fifth. And 2 to the fifth divided by itself is 1. So that 2 to the 0 equals 1 rule is forced upon us if we want this addition of exponents rule to continue to hold even when one of the exponents is a 0. Okay, likewise, we can use that same rule to explain the negative exponents. For example, according to that rule, 2 to the negative fifth times 2 to the positive fifth should be 2 to the negative 5 plus 5, adding up the exponents, which is 2 to the 0, which we just discovered is 1. So in other words, 2 to the negative fifth times 2 to the positive fifth must come out to be 1. Well, if I divide both sides by 2 to the fifth, then what I get here algebraically is 2 to the negative fifth must be 1 over 2 to the positive fifth. And there's nothing special about this 5. This works with any integer. You can replace 5 with 4 or 17 or whatever you want. So again, this rule about having this negative exponent is forced upon us if we want this rule to hold about adding the exponents. Okay, thanks for watching.